each pairwise intersections and all triple intersections are path connected. Also, they all contain their base point x0. And the statement that this is isomorphic to a free product of fundamental groups of these subspaces, quotient by a normal subgroup generated by the following relations. Relations telling that this combination is identity, where omega is the element fundamental group of intersection of a pair of them, and then of J alpha beta is a map from, write it like this, so J push forward of the corresponding conclusion into alpha, and J beta alpha is a push forward of the inclusion of this intersection in beta. Essentially, this tells you that, so again, so behind all the technical details, the idea is that, okay, first of all, any path can be any loop in X up to homotopy can be split into a composition of loops containing in A alphas, so that any element here can be understood as a composition of elements in this pi 1, and but there is some sort of ambiguity of defining this ambiguity, and the statement tells us the ambiguity is exactly all possible ambiguities are counted in by just possibility of changing, like if I have a piece or a loop living in the intersection, we can kind of treat it equivalently as an element of pi 1 of one of these sets or pi 1 of the other sets. So we can do this exchange, essentially equivalent, which in such exchanges is generated by multiplications by the elements of this form. And the way we proved it essentially is that, okay, so we consider some loop F representing an element in the fundamental group, and assuming that, okay, there might be some other loop F prime, which represents the same class, but then there should be a path homotopy between them, which is a map from a square to X. And so that on bottom we have F, on top we have F prime, and then we kind of using the continuity of our homotopy and the compactness, we can always split this square into kind of small rectangles, and then we consider kind of a sequence of paths like this, going between rectangles, and we show that each change, once you kind of change path by a small rectangle, the only change is accounted in by kind of multiplications by the elements of this form. Okay, and okay, today we will see some particular applications theorem. So how can one use it? And the first application is the following. So let X be a wedge product of some topological spaces Y alpha, and for which, so how we define this wedge product? So what we fix point, let's say Y alpha, for each of these spaces, and then we declare, then we introduce our equivalence relation on the disjoint union of the spaces, which tells us that all these points are equivalent. So Y beta is equivalent to Y alpha for any alpha beta, and then we define, this is can be defined as a quotient of this disjoint union by this equivalence relation. So it is just if you have a bunch of spaces, let's say Y1, Y2, and you pick, suppose there are just two of them, and you pick 2 points there, and what you do is just glue these two spaces just along these 2 points. So this would be these points. Okay, and we will also make the following assumption. Suppose Y alpha for each alpha has an open neighborhood, let's say U alpha capital Y alpha, look something like this here, neighborhood 1, and this is some neighborhood 2, so that these neighborhoods can be a deformation retracted to Y alpha itself. There is a, essentially you can this is a contractible, these neighborhoods are contractible, and there's a deformation retract which collapses them to these fixed points. This is understood as 1 point, as usual. For deformation retract defined for some subspace, this is a 1 point subspace in U alpha. So we make this assumption, and then statement that the pi1 of x, so here we consider a base point x0 is an equivalence class of our fixed points, chosen points Y alpha in our topological spaces, capital Y alpha, which are all identified, so it doesn't matter which Y alpha we take here. And so we take it as our base point in our wedge product. It's just a class of pair points in this example. And statement that, yeah, in this case, the fundamental group of X is just a wedge product of, is just a free product of fundamental groups of these individual topological spaces, Y alphas being the corresponding base points. So how does this follow from the one compens theorem? So, okay, so to use one compens theorem, we need to consider open cover by some open sets, which we denote with capital A alpha. And here we just choose, so this, in this case, our subspaces will be just labeled by the same alpha as we have in the definition of the wedge product. And so A alpha we define to be the same as Y alpha together with the wedge product of the wedge products of U beta, where beta runs over all indices, all possible values except alpha. So for example, here, if I take, in this picture, if I take A1, so this is the whole Y1 together with this neighborhood, which we chose in other sets. And if you have some another, we can possibly have another space, Y3. Automatically, we can denote as the same. Y, show it similarly. So, 3, neighborhood here. And so, of course, all these points are identified together in the wedge product. And A1 also includes this neighborhood. Of course, since all these neighborhoods, the deformation retract to just the points along which we glue everything, together this A alpha deformation retracts to just Y alpha, well understood as a canonical. So Y alpha can be canonically understood as a certain subspace in X. And so this is just because, okay, we can deformation retract everything here to points and change nothing here. So this will be our deformation retract from A1 to Y1 here. And this in particular means that the pi 1, so we know that, so A alpha, this means it's homotopy equivalent to Y alpha, and this means their fundamental groups, they are the same. Isomorphic, where isomorphism is given by the inclusion of Y alpha in A alpha.
No, I think retraction, deformation retraction is isomorphism, not deformation retraction.
Well, the retraction is a homotopy, right?
Yes, it derives what gammomorphism between these groups. In this case.
Well, you have a retraction map. Like, let me remind you. So you have A. So the situation when you define the deformation retract, you have A. There is inclusion map into larger space X, and you have a retraction R. And the statement that the statement that I composed with R is identity on A. And moreover, when you have a deformation retraction, you have a homotopy between the composition of R with I with identity at X, right? It's just a reminder. This means that R and I, they're homotopy inverses. So either I or R, they're both homotopy equivalences. Well, in this case, I mean, the notation might be a bit confusing. Here we're considering the largest space. Here, the smallest space is A alpha in our setting, and this space is Y alpha. Okay, and good. Of course, you also have a property that this A alpha, the union of all A alphas is the whole space X, right? And because it contains all Y alphas automatically, and then it contains all points in our X. So what about then when we consider one compensator, we also need to consider intersections. And well, of course, yeah, maybe I didn't mention this. We consider all these, for simplicity, yeah, we assume that they all path connected. Then X is, of course, will be path connected. So you consider, if you consider intersection of A alpha and A beta, this will be given. So by construction, this will be just wedge product of all our neighborhoods U gamma. Right? Because if you, here, for example, if you consider intersection of A1 and similarly defined A2, the only common points will be these neighborhoods. And this is, so all these U gammas, they are contractible, and then for the wedge product is also contractible. So we can simultaneously contract all of them, right? To this, to their common point. This is contractible. And in particular, this means that phi1 of any pairwise intersection, well, when alpha is not equal to beta, is trivial. So there is no, there will be no denominator in one-compens theorem, and it follows that then just phi1 of X isomorphic to a wedge product phi1 proof. But here we have nothing to divide because these relations, they are the set of relations which we have to consider is empty. Any questions? So So now you can see a more concrete case of this example where, for example, X is a wedge product of a bunch of, let's say, n copies of a circle. It looks something like this. N equals 4. 4 copies of a circle glued together at one point. So this means that y1 of x is isomorphic to a free product of n copies of fundamental groups of the circle, which we know is isomorphic to z. And this means that the result is just free product of n copies of z here. And so how we geometrically understand this is that, okay, so here an arbitrary, how does the elements in this free product look like? So this is just, so this thing is just a free group, a sort of free group generated by, let's say, A1, A2, AN. So there are n generators. And there is no relations, so this is a free group. So elements here are just arbitrary words constructed from this from the powers of these generators. So then, yeah, what I meant here, free group, I already wrote this. What I meant is no relations. For example, I can take anything like A1 to the 2, A2 to the 3, A3 to something like -4, and so on. And we know that for a circle, we know that if you have just a single circle, say the first one, A1 to the n, corresponds to a loop which goes n times around this circle. So here we just we see that any word corresponds to we're going to first go 2 times around the first loop, then 3 times around the second loop, around the second circle, and -4 times around the third circle, and so on. I mean, then you can again, for example, go A2 to the 2, and so on. And you can kind of intuitively you can see that this is indeed what happens. Like if you consider all possible paths up to homotopy, this is what you have. Any questions? Okay, so these are examples. There is no actually. Yeah, the result is just a free product. There is no these kind of relations coming from the intersections. Now we consider a more complicated example, and so this is something which is already appeared in homework. So let X be genus G. G is some positive well, non-negative integer. Well, for simplicity, assume that it's positive. Genus G oriented closed surface. G0, this is just a sphere. G1, torus. G2, something like this. So on, G3. Like this. And we want to calculate fundamental group of this X. Well, we already know the results for these two things. So here we know that the fundamental group is trivial. And here we know that this is Z square, right? Because this is also can be understood as a product of two circles. And for each circle, the fundamental group is Z. What about these guys? Okay, so again, we will use this the realization of the surface by quotient of a polygon. So let me remind you how this works. So well, let me see this here. So here, for example, we can cut it along this cycle and cut it along this cycle. And what we get, the rectangle where we have to identify horizontal, pairwise identify horizontal edges and vertical edges. Here, similarly, I can cut it along the 4 cycles like this. Then you will see if you do this, if you cut it, yeah, they all these loops, they all start at the same point. So here, for example, this point, the common point is just this vertex, these either of these 4 vertices, so they are all identified when we glue it back. And here, yeah, the picture looks, so we get an octagon. If I denote this cycle as A1, the red one, and the second red one, 2, green one says B1 and B2. I get the form B1 B1. This will be B2. This will also be 2. One. This will be two. Well, at least up to overall, up to change errors. I mean simultaneous change of the errors, and so on. So in general, you have a 2G, 4G gone. So we can use this representation to calculate fundamental group. So let me, for this I will probably need a bigger picture. Okay, yeah, in general, I will have something like this. 1, 1, B1 in the opposite direction, 1 also in the opposite direction. Then I continue with B2, 2, two in the opposite direction, then 2 in the opposite direction, and so on. And finally, at the very end, I will have A, G. Okay, and so again, these arrows just tells us how this, and the letters tells us how these edges are glued together, pairwise, pairwisely. And so let me consider some point, let's say y, inside this, inside the inside the polygon, and well, okay, this is a yeah, okay, this is a obviously path-connected topological space, so it doesn't matter where we choose our base point. And so what we do is the following. Again, so this X we represent as this 4G gone model equivalence relation, which tells us how we glue the edges pairwise. And we will cover our X by 2 open subsets. So first, one of them will be just our x, sorry, minus this point y, which we chose somewhere. And A2 will be a small disk containing, small disk centered at this y. And without loss of generality, I can assume that it contains some base point, which we'll use to consider the fundamental group. So without loss of generality, I can assume that x0, our base point, is somewhere inside this disk. Again, this will be our space, subspace A2, and A1 is a complement of this point y. Obviously cover everything. Okay, so now we want to consider, so to use Van Gamma's theorem, first we have to check that these are path connected. Okay, this is obvious. They are both A1 and A2 are path connected. And what about the intersections? Okay, the intersection is a disk without this point, which is anomalous, essentially, and it's also obviously path connected. So this is good. And then we want to calculate the fundamental groups of these individual guys and also fundamental group of the intersection. So first, the simplest thing is to calculate phi1 of A2. Well, this is trivial because A2 is homomorphic to a two-dimensional disk, and this we know is homotopic to a point. So it's a contractible space, so it's trivial. What about let's see, the next, consider pi1 of A1. So A1 is this surface without a point, and this was already actually in one of the homeworks to show that this is deformation retracts to a wedge product of 2G circles. So we know that this is homotopy equivalent write it here. Homotopy equivalent to wedge product of 2G copies of a circle. And how this is done is that when you remove a point, you can start just you can consider deformation retraction to the boundary of this polygon in a linear way by just following the rays starting from this point to the boundary. And so these 2G circles is just given by these edges with endpoints identified. 2G circles, one of them is just this HA1, another is HB1, then there is HA2, and so on. So there are 2G of them in total. And again, since we know the fundamental group of the switch products, this will be a free product of 2G copies of Z. And this is just a free group generated by alpha I, beta I, where I runs from 1 to G and no relations. So that so alpha I is represented by path going once around I. Alpha 1, for example, is a path going once around A1, and similarly beta I is a path going once around I. So before, just alpha I and beta I, they are generators corresponding to each of these circles. Okay, good. And finally, okay, now we want to understand pi 1 of the intersection. So this thing is a disk without a point, and this we know is a homotopy equivalent just a circle, right? Because the disk without a point, we can consider deformation reduction on a circle. We can consider deformation reduction on a circle, which suppose, for simplicity, passes through our point x0, which we chose here. Again, do this bilinear homotopy. So if you wish, there's a particular copy of the circle which is included in this disk without a point, and this is this copy of the circle which we have here. This means that this group is isomorphic to Z, and this has a single generator. Yes, it's free group no relation, and this corresponds to a path, so loop, class of a loop going once S1, copy of S1 which we have inside our disk minus a point. Okay. Now we need to understand these maps J's, which are push forwards of inclusion maps. So first, let's consider J12. So it will be a map from pi 1 of the intersection pi 1 of 1. And so this group is has a single generator omega, as we just argued. So it's enough to describe this map. It's enough to determine where this generator goes. But to determine this, so since we constructed from A1, we constructed a deformation. We consider a retraction to this boundary, which is the wedge product of circles. So then to determine, so we need to determine how this omega is written in terms of our generators alpha I and beta I. But then you just, since by definition of this push forward of inclusion, you just need to, okay, you first consider inclusion. This gives you a map, which omega corresponds to just a loop going once here, like this. And then you compose this loop, consider as a map from an interval to, from an interval, you consider a composition with this retraction. And then you will see that this loop, once you compose it with retraction, it will be a loop which goes along the perimeter of your polygon. And then if I go, if I, for example, consider, so you can consider, for example, starting. If I start from here, it follows first B1, and B1 corresponds to a generator beta 1. Then it follows A1, which corresponds to a generator alpha 1. But then it follows B1 in the opposite direction, so it corresponds to a generator B1 inverse. Then it follows A1 in the opposite direction. This means it corresponds to a generator alpha 1 inverse. Then it follows B2. This means here we have beta 2. And alpha 2, and then beta 2 inverse, then alpha 2 inverse, dot, and finally we will have alpha G. Again, to be more kind of specific, you can wonder, I can always choose my base point x0 so that it's this base point lies on the ray which goes to this point. No issue. Okay. Okay, so this was J12. What about J21? Well, J21 is trivial just because so it would be, in principle, you would need to consider a map from pi 1 of A1 intersection with A2 to pi 1 of A2, but this is trivial. So the map itself is trivial. So in particular, well, in the kind of multiplicative notation, J21 of omega is just identity, while J12 of omega is this non-trivial element. And so this is what we need to use in our relations, in relations which von Kampen's theorem tells us about. Finally, the result is pi1 power x isomorphic to, you can write it, well, let me write it. Have a So you have a free group. Well, you have a product. You have a kind of a trivial group, free product with a group. So this was pi1 of A2. This is pi1 of A1, 1, which is free group with 2G generators, which is denoted by alpha I, beta I, where I goes from 1 to G. And then we need a quotient about for all the subgroup generated by a normal subgroup generated by elements of this form, G1 to omega 1 omega inverse, where omega in pi1 of A1 intersection A2, this is Z. So it's enough, it has one generator, so it's enough to consider quotient just with respect to subgroup generated by this element where omega is a generator. And in other words, so this is 1. And this can be more compactly written. So if you remember, if you use this rather standard notation that the commutator of two elements in the group this thing, then this can be given the product of well, to make it, well, you can write it in principle, what you get is this thing. Equivalently, you can say that you have a group generated by this alpha I and beta I with a single relation given by the fact that this product of commutators is equal to 1. Well, okay, here the product. Well, actually, I will use. I can equivalently use inverse. Well, okay, I'm not going to bother. So I just write it. This is, of course, ordered product. So here in our convention, the A was going on the left, you start with G, and on the right, you end up at 1. So, well, usually it's written, yeah, well, up to choice, up to Up to redefinition of generators, this is the same as just having the more usual form of this. Have a commutator of alpha I and beta I, and this product is from 1. Well, because I can always redefine my generators by taking inverse of them and relabeling alpha and beta. So this is this result. So this gives you the result for fundamental group of a genus G surface, and this is used in a lot of places in mathematics. Well, let's check that for G equals 1, this agrees with what we had before for the torus.
Professor,
Yes?
is this group always free?
No, this is not free because the free, it has a relation. It has a bunch of generators and one relation.
No, for G equals to 1, it is free, right?
No, it's not free. It's well, it's free abelian group, but it's not a free group. There is still one relation. When G equals 1, there is still relation. Well, let me consider this case G equals 1. Phi 1 of x. From our result is just has 2 generators. Well, I can assume suppress the index. It will be just alpha and beta. Is a single relation alpha commutator is 1. But this means that arbitrary element in this group can be written always in the form alpha m beta n. Set where n, m are arbitrary integers. Because any word, so if I have an arbitrary word in some powers of alpha betas, I have a relation that the alpha beta commute with each other. I can always combine all alphas to the left and all betas to the right, and always bring it to this form. And of course, if I have when I multiply a pair of elements like this, so for m and n, and I take another element with m prime and n prime, again I can commute them to get alpha m plus m prime and beta prime. So with respect to group law, this nm, they just add up. So this group is just isomorphic to z squared, right? The direct product. This can be called a free but abelian group. The free as an abelian group, so it has a kind of free generators if you assume that it's abelian group, but it's not free, not a free group in a general sense. So this is indeed agrees with our previous calculation, which uses the fact that for G equals 1 you have a torus, and this is the product of two circles, and for product, the fundamental group is the product of the fundamental groups, and each of them is Z. Any questions? Well, if there are no questions, then we will start the next big topic, homology. But of course, this was a rather quite a brief introduction into theory of fundamental group. We didn't consider many other kind of applications. Fundamental group. So what was, okay, let me go back briefly to kind of big picture that we have. So pi 1 you can understand as following, well, the correct words are functor, but you can understand that you consider a collection of pointed topological spaces, and you consider them modular homotopy equivalence, and pi 1 for each of these topological spaces gives me a group. But if I consider a space up to a homotopy equivalence, this group is defined up to an isomorphism. And then you have some nice behavior, which essentially tells us that pi 1 is a functor. So if you have the map between two pair of topological spaces, this induces a map between the corresponding groups, which is what we call the push forward. And for homology, it will be quite similar. So we consider a collection of all topological spaces. Now, so one good thing about homology is that we are not going to, well, at least it's not necessarily to, in principle, to specify any point. Although there is a version of homology where you do specify point. Homology will provide us with a map to abelian, to the collection of all abelian groups. So homology will always give us abelian groups, unlike a fundamental group, which, as we saw in this example of the surface, can give us in general non-abelian groups. Modular, again, isomorphisms. Well, to be precise, this is what is called Z-graded. Meaning that there will be a kind of a collection, a family of, actually, of, for each topological space, there is a family of abelian groups in the labeled by integers. First part of our lecture course was about pi 1, and now it will be about homology. This homology theory will be kind of will be in a sense less geometrical, but more algebraic, and in a sense it will be easier because of this. Well, the kind of the good definition of homology is not quite geometrically intuitive. But what we'll start with is kind of a diva, kind of not a good definition of homology, and then we will modify it to make it good. But before, as usual, before we start doing anything, we need to introduce some definitions. And the first definition which we'll need is the definition of what is called the standard n simplex. N is a non-negative integer. Standard simplex formally defined as a subset Euclidean space R n plus 1. So we choose coordinates t0, t1 to the dot tn. And this subset is specified by the following conditions: that the sum of all coordinates from 0 to n is 1, together with inequality that they're all non-negative. How does this look for small n? Well, this is what you expect from simplex. So delta 0 is just, well, n equals, so you consider
Point. Just point 1.
Yeah, the answer is correct, but I want to show how this corresponds to this definition, general definition. So n is 0, so we have to consider R1 here, and we have just T0, and with the conditions that is equal to 1. Indeed, 1 point. So it's isomorphic to 1 point space. It should be by PT. Now, delta 1, again, if you want to understand the subspace in R2, so this you have equation T0 plus T1 is equal to 1, and you consider a positive quadrant. So this gives you this interval. Of course, it's homeomorphic, just a unit interval in this case. Delta 2. So for this general definition, you want to consider a subspace in R3. You can consider just a positive quadrant, positive subspace of positive coordinates. This would be this triangle given by equations 0 plus T1 plus these vertices, they lie on the axis at points with coordinates 1. And so on. Okay, delta 3, okay, if you want to use a definition, you would need to embed it into a 4-dimensional space, which is how to draw, but it's still, delta 3 is just homeomorphic to tetrahedron. Delta 2 was triangle, delta 3 is essentially tetrahedron. So it has delta n has in general n plus 1 vertices. This is the points which we usually denote by v with some index ranging from 0 to n, so that v0 in this representation where you understand the subspace of Rn plus 1, these are vertices with coordinates 1, 0, 0, 0, and so on. V1 is 0, 1, 0, 0, and so on till Vn for coordinates, but the last one is 0 and the last one is 1. This was kind of a standard simplex, and you can consider more generally you can see the delta n as the so let's consider vi, I again from 0 to n, to be points in some Rn, where n is greater and equal plus 1. And so that vi minus v0 for I greater than 0, so this is R n linearly independent vectors. And then we consider a simplex, which is kind of a non-standard in a sense, that which is for which these vi's will serve as vertices by defining it as the following subspace in this R capital N. Consider a sum of these vertices understood as vectors in Rn with coefficient Ti, and you impose the condition on Ti's the same as had before, that the sum of Ti's is 1, 0 to n plus 1, and they're all non-negative. And of course, this is there is so from this kind of simplex, there is unique linear homeomorphism to the canonical, sorry, to the standard. This is what we call standard simplex. Of course, it's just given by this linear, sorry, from the standard, homeomorphism from the standard. You just send the vertices which you had before in this standard simplex to the vertices we have here. So sometimes it's useful to use this more general thing, but sometimes we can use this standard simplex. But any questions? So yeah, another kind of part of our convention is that, that we can denote and simplex by the sequence of its vertices. And we want, usually we want to keep the order. Yeah, so our simplex will be, when we talk about simplexes, we usually assume that there is a particular order on vertices specified. Again, here, with a more general point of view, these vertices are just points in some Euclidean space. Fine, the fact that they are linearly independent, meaning that these, for example, if you consider two simplex in R3, this simplex, some triangle, actually here you can assume enough to assume this. Either it's R3 or R2, and you just want that this this statement is just this triangle is non-degenerate, for example, right? That these two vectors are linearly independent. You don't want okay, and okay, good. So this such, for example, n simplex, it has n minus m sub-simplices. Which are given essentially by restriction in the definition of the n simplex given by the subset this description given by the restriction of M coordinates are to be 0. And this means that this n minus m subsimplex has vertices the same as we had in our simplex, which we started with, but with m vertices removed. Usually, when we want to denote that the vertex is removed in this sequence, we will show a hat over it. For example, if we, so here we have a two simplex V0, V1, V2, and it contains, for example, one some simplex where we, for example, remove V1. And this notation just means that this is identical to saying that this is a simplex with two vertices. So this is our, so we remove V1 here, and this will be one simplex inside our two simplex. This. Particular case when m is 1, they're usually called some simplexes, the n minus 1 subsimplices. Are what is usually called faces of our original simplex. So here, okay, for a triangle, the face is actually an edge, but if you consider, for example, this simplex, tetrahedron, with vertices V0, V1, V2, V3. For example, we can consider a subsimplex where we remove the HV3. Again, just a notation means that V1 is actually the sequence of V1, V2, V0, V1, V2. This is indeed what is normally called a face of a tetrahedron. Any questions about these conventions? So what we first will define, what we do, we'll define what is called simplicial homology, which is kind of geometrically more clear what is going on, but it's actually harder to work with, in particular because you need to introduce additional structure on this, and this is what we call delta complex structure. But finally, we are actually what we will use instead, and what is all usually people use when we consider homology is we consider singular homology, and this extra structure is not going to be needed. So what is this? So a delta complex structure on a topological space X, the collection of maps delta alpha, sigma alpha. So the collection of maps labeled by some indices alpha. For each alpha, this is a map from n simplex to x. In general, n depends on alpha. So for different indices, this n can be different, satisfying the following properties. The three conditions. First condition is that sigma alpha, if we restrict it on an interior of our n simplex, injective for any alpha. And moreover, for any x, the capital in the topological space x, and for any point, there exists a unique alpha so that this x belongs to the image of the sigma alpha restricted on interior of the simplex and simplex where it's defined. If we consider restriction on the of these maps on interior of the simplices, there is a it is mapped to to some particular point x, and there only one map which gives us. Moreover, so on interior, these maps are one-to-one, the injective, and there are only one such map. Point of x. Second condition is that if you consider sigma alpha restricting on any face delta n, were defined. So this is, I remind you, the face is -1 simplex. This is equal to sigma beta for some beta. So this becomes, this coincides with another sigma in our collection of maps. So this is a map from n-1 simplex to x. Third condition, that if you consider some subspace in X, it is open if and only if its preimage and each sigma alpha is open or simplex. Essentially, this means that morally, this means that our X topological space X can be covered by all these simplices, so that for each point falls in interior only one of them. And so we consider, for example, two simplex in this picture. well, its boundary is some one simplex, and this one simplex is also well, the corresponding inclusion map is restriction coincide with the inclusion map for these one simplices. And the third statement is that the essentially topology of X is given by essentially gluing these simplices together. So the moral of this is that X is obtained by up to homomorphism is obtained by gluing simplices together along faces. Essentially, this kind of, you can understand roughly some triangulation of your topological space X. Well, in the next lecture, yeah, we'll give you some concrete examples and more so that this geometric meaning of this condition is more clear. Yeah, but for today we finish. But if there are any questions, let me know. Okay, if there are no questions, that's it for today.